Hello everyone, my name is Matthew Turner, and today we're going to be doing something a bit different. We're actually going to talk about my research into reducers. Now, this isn't going to be a full-on talk, it's more just going to be me casually chatting about things, but hopefully it will be of interest to you. Now, I know that most of you have already heard me talk about my research in some form or another, so this being part is going to be a bit redundant, but decorum mandates that I do it. Namely, what even is a reducer? Reducers, as we're looking at them, are a linguistic construct from Silk, which allows concurrent updates to a shared variable data structure. They are defined in terms of a monoid, a binary associative reduce operator. Examples are integration, list concatenation, and so on. They also have to have an identity element. Now, updates to a reducer are accumulated in modern as local views, which the Silk runtime combines automatically with the reduce operation when spawn computations sync. Now, if you felt that that was a tiny bit too abstract, let's look at a concrete example. Let's suppose we have a variable x that we're going to perform a number of updates to. Maybe those numbers and size are being generated by some function and it's being run on a loop iteration variable or something. Where it's not relevant, point is that it's an inherently sequential sequence of updates. Normally, we'd think that we can't really parallelize this. Or can we? Well, with the reducer, what we do is we split those operations in half. We don't really look at them because even though this is addition, we don't know that it's inherently commutative. And then we accumulate the values in x and x prime. Then at the very end, we merge them together. So there, we've made the normally unparallelizable parallel. And in fact, we can go even more complicated. We can look at 3 views. Really, there is no limit. Now that sounds pretty good. So that begs the question, why haven't you heard of these? Why does no one seem to use reducers? Now, luckily for us, there is, in fact, a alternative method to implementing hypermaps. This was introduced in Silk-M, and it was to use something called the sparse accumulator, or SPA data structure, in relation to the SPA conference. Now, a SPA consists of an array of values and an array containing an unordered log of the indices of any values that are non-zero. If you want to have zero-element values, sometimes you add a third array for valid values, but we don't really need to do that. Now, the data structure is initialized to an array of zeros, so there is our constant time creation of an empty hypermap. When an element is set to a non-zero value, its index is recorded in the log, and we increment the count of elements. And sequencing through the hypermap is accomplished by walking through the log and accessing each element in turn. If you're wondering when sequencing became important Don't worry, we'll get to that later. Now, with some very minor optimizations, by arranging the SPA data structures to serve as a hypermap, we can obtain the following key performance measures. First off, we can perform a lookup in constant time, and second, we can perform a sequence in linear time. Now, to implement this, we need to discuss our actual data structure underlying it. The SPA hypermap with a capacity of n views will contain the following fields: a view array of n elements, where each element is a pair of pointers to a local view and its landlord. Second, we'll have a log array of half that many elements. Each of those will have a 2-byte value indicating the index of an element in the view array. We'll also store the value of n, which is also a 2-byte int16. We'll have the 2-byte number of valid elements in the view array, and we'll have the 2-byte number of logs in the log array. That sounds relatively simple. Now, empty elements in the view array are represented with a pair of null pointers, hence the zero initialization being lazy. Whenever a new reducer is registered, the following sequence of events occurs. First off, the reducer's index in the view array is globally assigned. We have an ID manager, and we store that in a field called IDnum. And then the corresponding slot in the view array is allocated. We set the pointer to the landlord and the pointer to the local view. And finally, when the reducer is destroyed, the 16-byte slot in the view array is recycled. As I said, looking at things in a SPA map is more or less constant time. It requires 3 memory accesses and a predictable branch. First, we have to get the actual current SPA map. Now, full disclosure, as that is currently implemented, it is a call to pthread's thread local memory system, which is a bit more complicated. We'll have that narrowed down to a proper single memory access relatively quickly. Next, we get the ID number for the reducer object. Then we access the ID number view of the view array. Again, modulo some arithmetic, this is all just one memory access each. And then finally, we check whether the view guide is valid. Remember, if it's valid, it will be non-null. And the common case is that it is valid because after we have a failed lookup, we put something in there, and that only occurs at most once per reducer per steal. Now, to see the sequencing result, that is also relatively simple. If the number of logs we have is entirely contained in the log array, well, we just walk through the log array to get every element. And if that isn't the case, then we just sequence through the entire view array. Given that we have that 2-to-1 size difference, the thought is that the S3 cost is amortized against the cost of inserting views into the SPA map. So that all sounds pretty nice and good, but how does it actually perform? Well, Luckily, we've implemented this and have run a few key micro-benchmarks on it, and we get these results. Now, what you're seeing here is a bunch of tests. Just about all of them are some form of looping over an integer and adding to it in parallel. The exceptions are interest, which is obviously creating a list of integers, and zero sum, which doesn't actually use a reducer. It's just a measure of the overhead of the runtime system. So with that in mind, we see that we get speedups from anywhere from around 10% all the way up to 159%. I'd say that's pretty great. But remember, this is only one of the two issues I mentioned with reducers in terms of performance. The other is the internal scheduling mechanism for reducers, where one size really does not fit all. Now, before we go on, quick note of notation. When we say that we're reducing two hypermaps, what we mean is that we're reducing every integer in each of them and merging them all into the leftmost hypermap. This is where all that sequencing stuff becomes important. If we have to iterate through every reducer actively in LNR, we need to be able to do it quickly. Also keep in mind that this hypermerge is destructive. The right hypermap R there is completely right. With that in mind, let's look at how these things are actually implemented. Right now, the reducer hypermaps are effectively stored in closures. Each closure has three hypermaps, called the user hypermap, the right hypermap, and the children hypermap. User is exactly what you'd expect. It's for the user, the programmer, to look up the actual values of reducers. The children hypermap contains the accumulated results of completed child frames. These views have not yet been reduced into the user hypermap to avoid races. And of course, the right hypermap contains the same, except instead of completing child frames, it's right siblings, frames that come after the current frame in the serial execution. Now, whenever a top-level closure is usually created, all three of these are empty at first. We update these hypermaps in the following situations. First off is when we look something up and find that there is no valid view. That's kind of a given since we have lazy hypermaps. We also update things whenever there's a steal, whenever there's a return from a call, a return from a spawn, and add a sync. That makes sense, at least intuitively. But let's see what actually happens at each of these. Now, the easiest of these cases is, of course, a lookup failure. As I said, that's kind of baked in with lazy hypermaps. And when that happens, we just insert an identity element into the hypermap for the given reducer. Pretty simple. Now, things get a bit more complicated with random work stealing. After a random steal operation succeeds, and we place a new closure into the victim, we do the following. the new closure gets the user map of its parent. The parent gets an empty user hypermap. It also gets an empty child hypermap and an empty write hypermap, which is to say, we initialize it as having nothing. Moreover, if we create any additional closures by promoting intermediary frames, they also get the same empty treatment. Basically, this just says that we're starting anew when we steal a parent closure. For a return from a call, let's recycle that notation where C is a child frame and P a parent frame. We really have two cases here. If C is a stack frame, we can do nothing because they both belong to the same closure. Might be P, might be something higher up. Either way, we already know what's going on. Now, if C is a closure, then we transfer ownership of the child views to the parent by updating the parent's user map to be the child's user map. The other two hypermaps of C are guaranteed to be empty and don't participate. Now, what if we're returning from a spawn? This one actually gets pretty complicated. We're going to use that same notation again, and in the case where it's a stack frame, we again do nothing. Same reasoning. Now, if C is a closure, then we're going to reduce the views of all completed right siblings of C into its own views. We're going to do this update. Then we have two further subcases. If C has a left sibling error, we move C's user map into L's right map. And if C is the leftmost child, then we move its user map into P's child map. Now, if you were paying very close attention, you might have noticed a tiny race there. There's a race between C reading its right map and the right sibling of C, if there is one, trying to write to C's right map. Resolving this race is a bit of a delicate matter that I have no desire to go into because, trust me, it's a pain. Finally, we have the search sync case. When the frame P executes a sync, one of two things happens. If P is a stack frame, as I'm sure you're used to by now, do nothing. Same reason we always have. And if it's a closure, then after it passes the search sync statement, but before we execute any user code, we reduce our reducers of completed children into the parent. That's right, we merge children user into the user. Now what can we change here? Because if you're like me, you'll notice that this is a fairly rigid system. It works great for associative reducers, but there are a lot of variables we can tweak. Well, first thing we can do is we could make things less lazy. We could make it so that hypermaps are automatically populated. This would completely get rid of the lookup failure case. Sometimes this is a good idea, sometimes it's not. Either way, the option isn't there right now. Additionally, we could make things more easy when we merge everything together. Rather than actually merging it, we could just keep a unmodified tree that we could then merge later on. This is lazy merging, and sometimes it can speed things up when we're dealing with particularly weird reduce mechanisms. Again, it would be a great idea to have as an option. It's not there right now. Third, we could get rid of all of this scheduling machinery altogether. We can do that if we assume that the reduce operation is not just associative but commutative. This is where the bulk of my recent research has gone. The key observation for these commutative reducers is that we don't need to have 3 hypermaps per closure. In fact, we can get it down to having 1 user hypermap per worker, not per closure, because since everything is commutative and we don't actually need to keep track of the order in which things are merged, we can just have each lookup access the workers hypermap and then merge them all together at the end of the computation with an explicit collect call. Now, there are some subtle difficulties with this approach. First off is that care must be taken with that aforementioned collect call. It is on the programmer now, not the runtime, to make sure they call collect at an appropriate time. If you call it before your computation on that reducer is done, things break pretty horribly. There are also some concurrency concerns when we merge all of the workers' commutative hypermaps together. Namely, there's a bit of an issue where if one reducer is still operating, when the first one is merged, we can run into a bit of racy behavior where we're trying to retrieve the value of the view in one hypermap as the view of the other reducer is being added to that same hypermap. There are a handful of different ways around this. For one, we can have a relatively simple locking system. We can make sure the hypermaps are all concurrently accessible. There is a lot of research into concurrent hash maps out there that we could use. And we could use a directory system. We're working on implementing all of these and comparing them in terms of performance. That all begs the question, why do we care about these commutative hypermaps? Well, first off, as I said, they kind of strip out almost all of this supporting scheduling infrastructure, so that's a win. But we're also pretty sure that they cause an asymptotic increase in performance. That's right, actual theoretical performance. Yes, I still know how to do that. Do we have that result? Not immediately, largely because I ran out of time. Anyway, any questions?